Okie dokie, we're recording. All right, let's get started. Welcome back to CS 152. If you aren't taking CS 152, you might want to vacate now. Welcome back to all those who are. Okay, we're going to continue where we left off yesterday. I'm going to just insert a few brief administrivia that have kind of arisen from questions from students, et cetera, in the past 2 days, and then we'll get on with the history of processor architecture and get into microprogramming. So just a few things. If you look on the course catalog page and look at it under CS 152, you'll see class notes, time conflicts will be allowed, lecture will be recorded, no final exam. Bullet 3 for 152 is most definitely wrong. Bullet 1 is in a transient state right now because if you recall from last lecture, I said that for lectures at least, we will not be tolerating conflicts, and really the idea is that you come into lecture and that the recordings are just kind of an auxiliary for you to go back afterwards as opposed to watch as like a first-hand lecture. But we are in the process of trying to clear a wait list, which is actually as large as the current enrollment in the class. So we're trying to figure out how to clear this wait list. We know that a lot of people want to take this class, and we want to enable as many people who want to take the class to take it as we can logistically provide. This is still a work in progress. We're trying to get permission to grow the class. It's a little complicated. We need to get permission to hire additional TAs, GSIs. We need to make sure that there's additional discussion rooms that can hold people and that we're not going to be creating a fire hazard in either the lecture hall or the discussion section. We are working through this. I expect that the wait list will be completely processed by end of day on Saturday, or this is my sincerest hope. Now, depending on how much of the wait list we were able to clear, bullet 1 may not be, or the converse of bullet 1, the reverse of bullet 1, negation, which is what is currently in the syllabus as of last lecture, may not be tenable, because if we enroll twice as many students as we have room in this class, this physical classroom, then we're going to have to permit course conflicts. So stay tuned. We're erring on the side of admitting more people, even if it causes us to kind of relax this policy, but this is a work in progress, and we hope to have it done, like I said before, by the end of Saturday. Okay, next, Ed status. Everyone who's currently enrolled in the class will be invited to Ed by the end of today. As soon as we clear the wait list, which, like I said, will be at the latest end of day Saturday, we'll invite the waitlisted students to Ed. No one has been cleared from the waitlist so far. So if you sent me an email in the past few days, thank you very much. It's going to help me process the waitlist. If you are still on the waitlist and you sent me an email, do not be surprised because I've not cleared anyone. So worry not. Finally, slight modifications have been made to the lecture 1 slides that were posted to the website Tuesday at like 8 a.m. Mainly to the stuff in the lecture 1 slides that we haven't covered yet. So if you downloaded those slides, feel free to snapshot them again to get a slightly up-to-date copy. No big changes, so you don't have to do it. You'll miss out on like a slide or two and a little bit of text, but I just thought that I might give a heads up. All right, any administrative related questions? There is a final exam, so bullet 3 is just wrong. It is wrong for 152. This text came off of the 152 course catalog. For 152, there is a final exam. For 252A, there is not a final exam. There is a project instead. Good? Okay. Any other questions? Yeah. I apologize. This is really confusing because this class is a heterogeneous class with 2 subclasses, and in addition to that, there's this transient business with the waitlist. I'll simplify. There's a final for 152. There is not a final for 252A. There is no time conflict that is going to happen for the final exam in 152. Time conflicts for lecture are in a transient state. We're trying to figure out whether we will be able to say no time conflicts allowed based on how many people we let in on the wait list. But what I can say for now is bullet 3 is wrong for 152. That bullet really corresponds to a 252A. And bullet 1, just wait and we'll settle it in a few days. And bullet 2 is correct. There will be recordings for everyone regardless. Any other questions? Okie dokie. All right. And where's my mouse? Here it is. Okie dokie. So we were almost done with administrivia last time. So let's just finish that off and say a little bit about risk 5. I'm going to say very little about risk 5 on the slide because we're going to see it at the start at about the midway point in this lecture. But suffice to say, risk 5, like was probably the case for CS61C, is also the class ISA for 152 and 252A. It's a new, simple, clean, extensible ISA that was developed at Berkeley circa 2010, right as I graduated undergrad, as a matter of fact. Both of the dominant ISAs that are used in many commercial products today are a bit non-ideal for classroom use. If anyone has read and had to work with x86 assembly, I challenge you, even if you have done that, to recall the difference between AT&T and Intel syntax, and that's not even getting into memory mode addressing and all of the other issues with x86. And even ARM has some kind of non-idealities from an educational perspective. So we're going to do risk 5. Risk 5 has kind of like the best of both worlds. It's relatively simple, it's clean, it's extensible. It is actually being used in commercial products, so there's a real practical reason for learning it. There's a lot of documentation and infrastructure that's been built around RISC-V, not only here at Berkeley, but also in a variety of companies, notably Sci5, which was a spinoff of the Berkeley Architecture Group. NVIDIA's using it. India has made it a number of years ago, the country ISA. I didn't realize that countries had an ISA, but apparently just like countries have birds, countries now are starting to have ISAs, and RISC-V is, or at least was a number of years ago, RISC-V. I don't know what they would change it to. And it is being used by quite a large number of companies, even beyond that. Okay, for the labs, we'll be working with Chisel. So Chisel is a language embedded in Scala. If anyone has or knows Java, which I believe, or at least was, the language of choice in CS61B 13 years ago, everything that you wanted Java to be that Java just wasn't quite is what Scala is. So a nice language, multi-paradigm, incorporating a lot of functional ideas. And circa 2010, Chisel was developed to be a higher level hardware description language so that you wouldn't have to work with Verilog when designing RISC-V parts. So you're going to be interfacing with Chisel a bit throughout the semester. We're going to give you Chisel code, and you'll be able to kind of modify processor pipelines based on their Chisel code. You'll also be looking at the Verilog generated by Chisel. Verilog is a lower level hardware description language. You can kind of think of Verilog as like the assembly language for hardware, and Chisel as the C language for hardware. So it's not like the Ruby language for hardware, which would be like HLS, high-level synthesis tools, but it gives us a nice lift in productivity relative to writing low-level Verilog. If anyone has taken 151 and did an initial implementation for their project and realized that they wanted to change something, you might recall that changing things in Verilog is non-trivial. So we'll be working with Chisel. Chisel starts with a language and can be compiled to multiple backends, one of which is like Verilog targeting FPGAs, another which is Verilog or another low-level HDL targeting ASICs, so it's quite modular, another nice language to have in your toolkit when you graduate. Okay, I just did questions, so in 2 seconds, if anyone has a question, shoot your hand up, otherwise we will get on with the show. Okay. All right. So for the next, I want to say like 30, 40 minutes, we're going to give a yes. Ah, sure. Yeah, this didn't happen yesterday, so I get rid of it. Let me try unsharing and then we'll see if we can fix it. Okay. Oh, really? Okay, let me just try that. Alt A, you said? Okay, okay. Let me go more. Let's do it. If anyone sees the option, just tell me what the words are. Hide video panel, floating meeting controls. Hooray! Thank you. I would have not noticed that until the end of the semester. Okay. All right. So for the next 30 or so minutes, we're going to give a whirlwind tour of processor architecture history. This is going back 200 years, even though almost all of the progress has been made in the last 100 years, which when you think about it is kind of incredible. So we're going to be going through a lot of old ideas. Why are we interested in old ideas? So it helps to illustrate the design process to give you a sense for what the first principles thinking was at the time. It's not that we were handed the current processors and we don't know the sequence of thoughts that went into bringing us to the way that we design pipelines today. We're going to go back to essentially when people lived on desert islands and all they had to get off the desert island was a bag of transistors, and they had to, based on the technology at hand, kind of figure out how to get things working. So first principles thinking. It turns out the core concepts in computer architecture don't change, but they do change in form. So for example, locality, prediction, speculation, specialization, indirection, parallelism. These concepts come up in ebbs and flows throughout the design of processors in various forms and in reaction to technology changes. So when technology changes happen and trade-offs therefore change in how you design a machine, we invoke these concepts to improve efficiency, functionality, robustness, etc. Because future technologies might be as constrained or less constrained as previous ones, so kind of like harking on what I just said. And of course, there's the old adage, those who ignore history are doomed to repeat it. If anyone goes on to architecture research and tries to reinvent indirection, for example, it's probably not what you want to be spending your graduate years on, so it's good to know what people have been doing for the last 200 years. Okay, and where's my mouse? Can I get my mouse back? Great. All right, so before we do this whirlwind tour through processor design, I think it's good to step back and shine a spotlight on the main concepts that have been developed in the past 200 years, the main kind of steps, so to speak, from initial machines to what we think of like modern processor design today. So one that I want you to pay attention to in the following slides is what the set of operations and the set of reconfigurability is offered by the machine. So we have ISAs today, ISAs. We have x86, we have ARM, we have RISC-V, we have a bunch of others. And while they have a ton of different instructions that do different things, it turns out that there's only really 3 types of core fundamental operations that when you kind of boil these ISAs down really matter. And this is broad strokes, but again, this is to give you a sense for what to look for in future slides. And those kind of broad strokes are, we need arithmetic. If we can't do arithmetic, then there's not much that the machine's going to be able to do except heat up an egg if you were to place an egg on top of the socket. We would nominally like data-dependent or conditional branching. And finally, we would like data-dependent memory addressing. So arithmetic, branching, memory accesses. Just out of curiosity, what subset of these three things do you think we really need to run any program that one could imagine, or as we'll soon define, is computable? Do we need all three of these, or can we get away with a subset? Yeah. You're mostly right. So I actually, I put adjectives before these words very carefully, but the adjectives matter. You need memory addressing, but you don't necessarily need data-dependent memory addressing. On the other hand, you do need arithmetic. Per what I said before, I was not lying. All you'd be able to do without arithmetic is heat up an egg. Do we think we need conditional branching? We didn't say anything about that. Do we think that all we need is arithmetic? It certainly would seem so, right? It would be a major drag to write a program without conditional branches. Does anybody want to venture a hypothesis that we don't need conditional branching? Yeah. That's I'm translating what I think was said in CS61C on the fly. I think that's it. So the answer is you don't need conditional branching. So very quickly, how ridiculously annoying is this going to be? Can people see this? Is that like big enough, or do people on this side of the room, it's completely hopeless? Push this back. I just wrote if X. The color is good or bad? Bad? Okay. I'll describe this verbally. One way to implement a branch is like we're all used to. If some condition is true, like let's say condition, this variable X is true, assign some value to, let's say, a destination register that we'll call D. And if the condition is not true, then don't assign that value to D. This is how we normally think of conditional branching in machines today. We don't need to have a branch to do this. We can implement this using multiply and add. So if anyone has taken CS61C or CS151, you know what a multiplexer is? Raise your hand if you've heard the term multiplexer. Okay, everybody has heard the term multiplexer. A multiplexer, recall, is made up of a few OR gates and an AND gate. OR gates are like add, AND gates are like multiply, and you can write what is semantically the same as a multiplexer in software using only arithmetic, using a composition of add and multiply. The idea being that if a destination value can be assigned to a different source value on both sides of the branch, and you need to choose which of the values will update the destination depending on the predicate of the branch. You can express that using arithmetic with something of the form predicate times source value that you wish to copy into the destination plus 1 minus predicate times the alternative value. This is what's called expressing programs as software circuits. If you've taken classes in theory, or for that matter, applied cryptography, or even high performance computing, you will see this idea come up because, well, it's very bad because you have to evaluate both sides of the branch or both inputs of the multiplexer to derive the output. It's regular in terms of its computation. It turns out that branches are hard to design for in a high-performance way. If you eliminate them, in certain situations, depending on the manufacturing technology, you'd be able to run a program faster. So it turns out you only need arithmetic to get the ability to write any program that I called before as computable. Now, we don't want to write programs that way. If you think about the amount of extra work that you'd have to do to evaluate a program that looks like a deeply nested sequence of if statements in this fashion where all you have is multiply and add, you could do in the worst case an exponential amount of work relative to the version that just had branching. So branching is awesome. but it's not necessary. Likewise, data-dependent memory addressing is also awesome, but it's not necessary. It's not necessary for the exact same reason that data-dependent branching is not necessary. The analog, when we're thinking of memory, is instead of having a way to take a variable in your program and use that to randomly access memory, which is data-dependent memory addressing, you can just run a bunch of load operations from memory with constant addresses, reading everything from memory, and then you choose which value you actually needed by doing a compare operator, which is a type of arithmetic, when that address actually comes out. It's the exact same software multiplexer type strategy. You get the same construction just out of multiply and add. But this is obscenely expensive. If you have a memory of n addresses, to do a single lookup, you need to access the entire memory as opposed to going just where you want. So we would really like to have these three things, but only the first is fundamental. Now, something interesting about viewing ISAs as these three pieces is that you can, if you squint your eyes, you can get a sense for the fundamental use cases of different architectures based on how well they support these three different types of operations. For example, CPUs today, very good at supporting all three. We have high performance branch predictors, we do dynamic branching really efficiently, we have the ability to send many loads out to memory simultaneously and out of order execution. We'll cover all of this later in the class. Yeah.
So you're saying,
Pardon me? Yes. Just the data dependent part. Yeah, just the data dependent part. Same with, yeah, it's a little bit different, good point, than the second bullet. The second bullet, you don't need any type of branching, whether it's data dependent or otherwise. Non-data dependent branching, though, is kind of no-oppy. So CPUs are good at all three of these things. GPUs are much less flexible with respect to dynamic branching. GPUs perform by far the best when you can give an assurance that many threads that are running on the GPU are going to be taking like branch decisions. So you can say that they have inflexibility in the way that they do data-dependent dynamic branching. On the other hand, they're very good at doing data-dependent memory accesses and have optimizations like dynamic memory coalescing for handling that case. If you go even simpler and you remove the ability to do data-dependent memory addressing, you get simpler architectures, closer to what the later slides call calculators, but we more call today DSPs, digital signal processors. Okay, so three core operations be on the lookout for. Stored program. Oh, and I should say, anything that can do arithmetic in a way that can be programmed so that you can express arbitrary programs that we deem computable or that has data-dependent dynamic branching or memory accesses, I'm going to informally call Turing complete. And we will come back to this in not much detail, but we'll touch on it in a few slides. Next concept, stored program. The idea that instead of having an explicit program, which is fed into a machine on punch cards or a plug board or something like this, I want to have a memory, and I want the program and the data to be thought of as the same thing in this memory. So this is a big idea. It is how all machines are built today. Interestingly, we'll see what the motivation was for stored program back in the day, but every machine is built like this, and it enables a bunch of cool hacks like self-modifying code, code portability, all sorts of neat stuff. Big idea, keep a lookout for it. Abstraction. Is the machine's implementation exposed to the programmer? Also be on the lookout for processor idioms that we use today. PC, pipeline stages, separation between code and data in some architectures. And then finally, the instruction set architecture, the separation between what the software sees about the hardware as a set of abstract operations and what the actual hardware is implemented or how it is actually implemented. And then finally, just because it's fun, and this is something that is like the ninja skill of a computer architect. Be on the lookout for technology-influenced design choices, for example, number representation and choice of operator, in the various designs that we're about to see. So really, the Swiss Army skill of a computer architect is being given a technology and a set of constraints and deciding what to do with it to implement a computation the most efficiently. And these different trade-offs motivate very different looking designs. Okay, so to start, way back in the day, we had analog computers. Analog computers are ones that represent problems or state as some physical quantity. For example, like the position of a gear, a voltage on a capacitor, some physical quantity, and it uses a physical process to directly calculate results. So there's this thing, the Antikythera mechanism, which was a way of predicting orbits and interesting events like eclipses, which modeled the system physically. This was one of the first found examples of an analog computer. Certain physical constructions of mechanical objects today, like airplanes, they'll use the properties of physics to improve their efficiency, like the way that wings curl to reduce drag in a plane. Now, this was popular way back in the day. It is, of course, still popular, like the wingtip vortice example. Interestingly, it's making a bit of a comeback as we push towards specialization to continue to get more efficiency in the wake of Dennard scaling, stopping, and Moore's law slowing down. It's making a comeback. So for example, everyone has heard of Ohm's law, taken some lower level electrical engineering class, V equals IR. So like you learn this relation and you're like, okay, that's interesting. That's going to help me solve a P set. A computer architect is going to look at this equation and see, oh, if I can read a voltage and I can control a current, and oh, by the way, I go to the hardware store and buy a resistor with a particular amount of resistance, I've just implemented multiply by a scalar. And multiply turns out to be one of the most important operators today for things like machine learning. And better yet, if you have a programmable resistor, then you've figured out how to implement multiply in a way that you can actually change what the scalar's value is. So you have something closer to true multiply. And this is just exploiting the physics of electronics. All right, well, with that all said, we're going to focus mostly on digital computers. So digital computers have some pros relative to analog. They represent problem variables as numbers encoded as in discrete steps. So there's like lines of a program or cycles of a processor. Everything kind of happens discrete, and abstraction makes things at least look like they're happening sequentially. And this is great because we don't have to deal with noise issues and errors the way that we do with analog devices. So we're going to stick with this paradigm because it enables us to think about how to build machines, kind of pushing the robustness problems down to lower in the stack. And it's, for the most part, not constrained by physical realizable functions, with the exception of like the fact that it is built on switches, whether those switches are relays or vacuum tubes or transistors or something. But it turns out that switches are a completely magical thing, and if you have a programmable switch, you can implement anything. So for all intents and purposes, they're not constrained by things that we can implement physically. And this is the focus of this class. Okay. All right, so first hero in computer architecture is this person named Charles Babbage. He was the Lucasian professor of mathematics at the University of Cambridge, which I believe was the same post that Newton held like 100 years before, if I'm remembering correctly. He was a true polymath and ahead of his time. And I'm not just saying that because the slides say it. Like, you'll get a sense by the end of this lecture, he was 100 years before anyone else. It was completely incredible. Where he got his start was the way that people were doing calculations for things like transcendental functions, like trig functions, where you'd have these big tables, and for discrete values, like if you have sine x, for different values of x, you just look up the row in the table corresponding to your value and you'd get the output out. And this is like bad because if your value is not there, then you have to do some interpolation where no one tells you what to do. Normally you don't do the interpolation, you just round, so it's kind of scuzzy. And if the values weren't calculated with enough precision, they might not be useful to you. In short, it was a bad state of affairs. So he invented the idea of mechanizing what humans that were called computers. Interestingly, this term of humans being called computers lasted until through World War II, but it was a thing back in the 1800s, mechanizing this process of people doing computation in a systematic way. And the first design or idea that he came up with to do this was this thing called the difference engine. This was when Beethoven was still alive. So it's like Beethoven is writing his Ninth Symphony, which is amazing, and Charles Babbage was designing the difference engine. So what the difference engine did was it tried to approximate continuous functions. So a continuous function, just like one that doesn't have breaks in it, you can, as it turns out, approximate these with polynomials. If you've ever taken an applied crypto class, polynomials are completely amazing. You can program them. They're like super cool, very flexible. And with a high degree enough polynomial, you can like sketch out arbitrary functions. How do you compute polynomials? What he found, or what he kind of exploited, I don't think that the algorithm was his idea, but the implementation of the difference engine or like obviously the concept of polynomials was not his idea, but the concept of the difference engine and its implementation was his idea. What he noticed was that if you had a polynomial, like let's say f of n squared plus n plus 41, something like this, and let's say furthermore that you want to evaluate this polynomial at multiple points. So if you've taken like, I can't remember whether it's like Math 7B or something like that, advanced calculus Taylor series. This is like something you'd like to do with a Taylor expansion or a Taylor series. It's like to calculate the value of a function at multiple points. What he exploited was that you could calculate the value of a polynomial at multiple points more efficiently than just kind of writing it all down for all of those points by first computing the difference between that polynomial's value for one value of input n and the previous value of input n, and then decomposing that into sub-differences. So again, think Taylor series. This is similar to taking a derivative. You take a derivative, you take a derivative again, and you go all the way down until your n, or I'll say k degree polynomial is a constant. And it turns out that there's a beautiful dynamic programming representation of computing the value of the polynomial at different points if you take these successive differences. And furthermore, this dynamic programming program only requires an adder to work. So the way you can kind of think about it is you take your polynomial, you write out a table with as many rows as the degree of the polynomial, because you get to take differences of differences of differences all the way to the end. And then you're going to, for the columns, write out the different values that you want to evaluate the polynomial over. And what you can do is use ideas from dynamic programming where you kind of like think about your computing landscape as like a grid, and nearest neighbor communication gives you the next value. The current value of a difference plus the next value of the next successive difference gives you the following value of the first difference. And so you can use this to calculate the d sub n's, and then more intuitively, you can start calculating the next values of the original function that you wanted, the original polynomial that you wanted to compute for. And this is just kind of bubbling up and memoizing results in a very kind of like DP fashion, using only addition. So only addition, fast evaluation of a polynomial at multiple points. This is perhaps the first example of algorithm hardware co-design, which is kind of like a very important thing in computer architecture nowadays, because we're having to specialize the entire stack to different problems. Super cool. And a really kind of testament to computer like the skills that a computer architect needs to have. Add is reasonable to mechanize. back in the 1800s. Multiply and divide and anything else, not so much. So forced to work with an adder, what can you do with it? Classic architecture. So he wasn't a builder. Someone else built this. There actually is an implementation in a museum of a difference engine. You can like crank it and it works. I don't remember how it was programmed, but if you visit Britain, make sure to see it. Now, even kind of like more incredible, he designed this thing, bits and pieces of it were implemented, but I don't think the entire thing was ever implemented. This thing called the analytic engine. So the analytic engine, this is really the star. The difference engine you can think of as like the first hardware accelerator because it only was able to evaluate like polynomials at multiple points. The analytic engine was this just revolutionary and far-reaching design that even 100 years later, when we were designing computers in the middle of World War II, this is 1837, they weren't as functional as the, or flexible or expressive as the analytic engine. So this is like recognized as the first general purpose digital computer. It has, recall the concepts that we were talking about previously, it's got many of the concepts from the previous slide on concepts. It's got memory, it's got arithmetic, it's got conditional branching. It was a really interesting way that they implemented conditional branching. I think that it was like they would actually like change the order of the program as it was inserted. It had a form of microcode, which we'll be learning about later today. The program was on punch cards, so it wasn't a stored program. You had your program on punch cards. The instructions in the punch cards look pretty much the same as instructions we have today. So you've got like 3 addresses, just straight to memory, no like register file. So like 2 operands, a destination, kind of what you'd expect. And branches were implemented by mechanically changing the order that the cards were inserted into the machine. But hey, conditional branching is conditional branching. Only small pieces were ever built. So just a few kind of interesting design choices. Storage was implemented using gears. So imagine you've got like a dial. Twist your head a little bit and imagine that that dial is a gear because gears can be automatically turned or mechanically turned. And every position of the gear represented a different like number in decimal or binary. Now, when you think about it, if your storage is a gear, binary makes no sense because it ain't human readable for one, unless you're like a code ninja 150 years later. And it's hard to imagine a binary gear. And so they just used decimal. That was perfectly fine for their purposes. They had 40-bit precision or 40-digit precision in base 10, which is really big. It's like over 133 bits. They got away with this, or they needed this much precision, whereas like our floating point representations are like 32-bit or 64-bit or something like that, because they didn't have floating point standards that gave any guarantees on discretization loss for an arbitrary number representable in a smaller space. So like Wilhelm Kahn, who is a professor here who won the Turing Award, was responsible for the IEEE floating point standard, and kind of the black magic behind that standard was coming up with a representation where for whatever number you wanted to represent, floating point would be able to do it pretty well in a limited number of bits. They didn't have that, and so the solution, the alternative was just use more storage. And it was kind of like fine because they weren't trying to follow Moore's law or anything back then. They didn't have competitors. So they used locking as mechanical amplification to overcome noise. So this is like as an engine, it's kind of like rumbling, and you need a way to like lock the gears so that like vibrations don't propagate and get out of hand. So this is kind of like a nonlinear gain in digital electronics today, but like all mechanical. And it had a fast anticipating carry adder. So one more time, those who have taken 151, ECS 151? Yeah, right. Okay, like half the class. So you've learned all about adders, like ripple adders and carry adders and cogstone adders and carry skip adders. This is an early implementation, which is akin to a carry propagate adder, which is one of the adders, if you recall, for getting the critical path, which is the carry under control. Okay, so about the same time as Charles Babbage, we have Ada Lovelace. So Ada Lovelace's story, another completely incredible person. Her story is like she started like on paper. She started by translating lectures of this guy named Luigi Menabrea and also Babbage. But saying that she translated or transcribed lectures does not do her justice. It's kind of like the story of like Fermat, like all of the goodies was in the margins. She would significantly expand on these lecture notes, coming up with insights that would just be visionary. Unfortunately, like no one really followed for 100 years, but you look back on it and you're like, she was 100 years ahead of her time. So she like wrote, I don't know if it was in the margins or just as kind of like an embellishment of the notes that she kind of expanded on, but she wrote a program to compute Bernoulli numbers using the analytic engine that actually worked, even though she never could run it because the analytic engine was never built. This is the first computer program. And she just otherwise imagined many use cases of computers, namely the analytic engine, was even inspired to do things like model the human brain. And this was back in the 1800s. Okay, next up, Alan Turing. So Alan Turing, this gets interesting because we've got many people coming up with similar ideas at around a similar time. Babbage was one of kind of the roots of knowledge. He's like the root of the general purpose computer. And as far as we know, he was the first. Alan Turing is like Babbage in that respect, except with respect to stored program computers. And if any of you have taken theoretical computer science, you know that that is not doing justice to Turing's contribution. So you may have heard of him before. The Turing Award, which is the Nobel Prize of Computer Science, is named after him, so he's got to be a big deal. He's considered by many to be the father of computer science. And one of his kind of like most significant contributions, which is still being used all the time today in theory, is this thing called a Turing machine. What's a Turing machine? A Turing machine is, for all intents and purposes, a theoretical but still processor. It's basically a processor designed by a theorist to test the limits of computation. But all of the core pieces that, going back to arithmetic, conditional branching, memory addressing, all of it is there. If you want to put it in the terminology of 152, you can think of it as the most heavily over microprogrammed computer ever designed. So what it was it was made up of a tape. A tape is like a bunch of cells. This is like your memory. Every cell is an address. Every cell holds 1 bit. So your data word size is 1 bit. There's a head that can move across the tape, 1 space to the left, 1 space to the right. You can see this picture here. This is like what they mean by tape. So just imagine that that's your memory space, this tape. And the head can kind of move across the tape. And at a given position, it can either read the value on the tape or it can write the value on the tape. And then finally, there was a state transition table inside kind of the brains of the machine, which people here know what a state machine is from 61C, I believe. Okay, good. It's a state machine that, given its current state and the current value that it reads at whatever the position of the head is on the tape, decides on a next state. This is your program memory, or that's a way to think about it. Your program is encoded in the state machine. So this is a Turing machine, incredibly influential. It turns out that this simple machine is compute isomorphic to any algorithm that we call computable today, which is to say anything that we can run on a real processor. So anything that we can run on a real processor, we can also run on a Turing machine with no more than polynomial slowdown. So very kind of like a profound way of thinking about computing, and it is a processor. And some of the ideas from it we will see later on. But he took the idea further. He took the idea further by proposing an extension called the universal Turing machine. The universal Turing machine is a flavor of Turing machine where the state machine in the brain was not an encoding of your program, but instead you could think of it as the control logic in a processor pipeline. And the program was encoded on the tape itself. So program on the tape, data on the tape, the state transition table is your processor pipeline logic. And this is, for all intents and purposes, the first stored program computer invented in 1937. Just goes to show how broad this guy was. Have people seen The Imitation Game? Movie on Alan Turing? Okay, so it doesn't focus on the Turing machine part, which is more his like deep contribution to computer science. But you may remember from that movie the big kind of machine with all of like the spinning things, or like the things that turned the bomba. I don't know if they called it that in the movie, but it was what was used to crack the German Enigma cipher machine. By basically, for a given subspace of possible encryption keys, searching all possible combinations. He also orchestrated the development of this machine in World War II. So in addition to coming up with profound theoretical contributions, he was also a builder, and he could also build these machines. So truly incredible guy. This was in the 30s, and continuing on with his work in World War II. Okay, so that kind of takes us, I jumped a little bit. So we went from Lovelace to Turing. We're now in kind of the mid 30s, and now we're in the 40s. And what's kind of incredible is that we're not building off of Babbage's stuff in the 40s. We've kind of taken a step back. And instead of general purpose computers, we're focusing on more fixed function computers, where the purpose is to do things fast. So this is like to crank out calculations for example, missile trajectories, or the design of the bomb as a part of the Manhattan Project. So the focus was on speed for fixed functions, and programmability was slowly being rediscovered, even though it had already been in the analytic engine, and Turing already gave us stored program computers a decade earlier. So there's just kind of like a few of these kind of like calculator-based machines. I'm going to kind of like zip through them. The first one is this Atanesov, I think that's how I pronounce his name, Berry linear equation solver. So fixed function, good at solving systems of linear equations, things that you wouldn't want to do by hand, like up to 29 simultaneous equations, so quite a thing, using like presumably matrix algebra. It had dynamic memory, a fixed drum of capacitors, kind of like the way that DRAM is built today, and used vacuum tubes, which were a switch as a precursor to the transistor for logic processing. There was a patent dispute. He and Eckert Mauchly, who we'll learn about in a second, were trying to get rights on the first programmable computer, and he like won the day, but that's a story for another day. Next, there was this thing called the Zeus C3, where the diff between the Zeus and the Adanoff-Berry machine was that this is actually starting to look more like a pipeline. So this is starting to look more like a computer. It's got floating point arithmetic, but it does not have conditional branching. It could still do all programs by doing that conversion from a branch to multiply add software multiplexer idea that I described earlier. And that was actually how they implemented some of the code that they ran on this machine. So they could reconfigure it through tape, but it was lacking conditional branches. So its speed for like general purpose computation was limited. It used relays. Relay is yet another type of kind of mechanical, pseudo-electromechanical switch, kind of like a precursor to the transistor. Next, we have the Harvard Mark I. This was in 1944, so clearly like kind of big. Proposed by this guy at Harvard, Howard Aiken. Mostly mechanical, as you can kind of infer from the picture, lots of gears, it weighed a lot. It stored 72 numbers with 23 decimal digits each. So what's kind of interesting is if you look at this picture, does anyone want to guess how many of these little circular things there are across? So 72 numbers, 23 digits each. How many of these little dials do you think are across? 23, exactly. I haven't verified that it's 72, but it goes off the page, so I assume that it is. So this is its memory. And you just look at this array. These are dials. It's kind of hard to see what they are, but they're dials that the machine can change and that you can change. And this is how you encode constants and other numbers inside the machine. Just to give you a sense, same idea with the bomb. If you remember the bomba from the Imitation Game, that's what all of those gears are along the front. Those are its program memory. So its speed is good, but it's not like incredible. It can do an add in less than a second. It can do a multiply in a few seconds. It can do a divide in a little bit slower time. It's faster than by hand, clearly, but it's nothing like the machines that we have today, or even the machines that came up like 2 years later. but just to kind of like take a note on its speed. You can implement loops by gluing the paper tape that you use to, or the paper tape that you use to represent the programs into literal loops, and it just kind of spins around in the machine and you get a loop. But again, it has no conditional branch. So again, we're kind of like taking a step back in terms of progress from the Babbage stuff. Babbage's work came into more of the spotlight later on, but people had lost track of it and were reinventing the wheel, and less well, if you will. So we still did not have conditional branching, and it kind of like mentioned Babbage, but it was more limited than the analytical engine. Okay, and so just to take a moment and say something about compute time. So like we have an add in 0.3 seconds, we have a multiply and a little bit more time. Again, the focus here was speed. We were interested in crunching numbers. So von Neumann is about to come into this story. Von Neumann was interested in machines that could do multiplies faster than he could in his head. This was his benchmark. And he could actually do multiplies very quickly in his head. So this was kind of like one of the main use cases of computers at this time. So now we have the ENIAC. ENIAC is the first electronic computer, the word electronic being kind of the key word here. So this was designed at UPenn by Eckert and Mauchly. Eckert and Mauchly, if you are in computer architecture and start doing research in the field, the highest award that you can get in computer architecture is the Eckert-Mauchly Award. So these two were very important. It was based mostly on vacuum tubes, switches for logic. It weighed a lot. It also took a lot of power. So interestingly enough, there's I think the largest form factor GPU that you can build is the DGX2. I think it costs like $100,000, but it does 2 petaflops of compute. That's 10 to the 15 floating point operations per second. That's a lot of compute to have in like a box this big. A DGX2 is 10 kilowatts. This is 150, and I assure you this was not 2 petaflops. 10 decimal digit accumulators. It had conditional branch. Finally, we learned from our mistakes. It was programmable. It used plug boards for reprogrammability, which if you think about programming a computer with plug boards, that's awful. But what was amazing about it was that because it was purely electronic, now we're starting to get really fast compute. So it was able to do a 10-digit by 10-digit multiply in 2.8 milliseconds. So now we're getting to the point where we can really start accelerating human progress. It was completely I/O bound because its pipeline was so fast, and it was always broken because these vacuum tubes don't turn out to be that robust. So here's a picture of it. These plug boards are how you programmed the thing. Kind of looks like the gadget from the movie Oppenheimer on steroids. It wasn't plug boards on the gadget. Those were just power cords, fueling or powering the charges, but kind of like similar mess. It took days to reprogram this thing. And that was really what led them to design the next machine, the EDVAC, which was where people started talking about stored program machines. It was so hard to reprogram the ENIAC. They wanted to be able to represent a program in memory, kind of go the whole 9 yards of really making code portable and modular, etc. So that was the EDVAC project. This intersected with John von Neumann. And so there's credit that's given to him for the stored program computer idea, but he will be the first to tell you that that was not his idea and that that was Alan Turing's idea. So this is like confusing because we have like von Neumann architecture and we credit him to the stored program computer. This is false. And he would be the first to tell you that. So they took the EDVAC design and they kind of backported it to the ENIAC. So the ENIAC was not such a pain to program. The ENIAC slowed down when they did that, but it was possible, which was interesting. And this thing was actually built in the early 1950s. Okay, I know these names are just lovely. We have the ENIAC, we have the EDVAC, we have the EDSAC. This is something that happens when you work on research. So the EDSAC is kind of the next machine in this generation. This is where a person named Maurice Wilkes comes into the picture. This is kind of the next generation stored program machine. It has 2's complement arithmetic. Everyone should be familiar with that from 61C. It has a simple accumulator ISA. with now that we have stored program computers, self-modifying code, because as soon as you have code in memory, immediately what you want to do to get more efficiency is start hacking the code directly, even though that kind of makes people's heads turn on fire. This machine was the first, this is where people really started thinking about programming principles and programming paradigms. So David Wheeler, who was the first PhD in computer science, invented the subroutine called the Wheeler jump. So this is this notion that we don't have to, when everybody wants to call a function, plug in different plug boards into to get access to that function. We can just write it to memory once and jump to it and maintain some state to understand where we have to jump back from. So really big leap in terms of programmability and abstractions for writing larger programs. And this was the first machine with a microprogrammed control unit. Maurice Wilkes was kind of like a pioneer in that space, and we will get back to that in a little bit. Okay, so the next few slides I'm going to just take us a little bit more on this journey, but kind of skipping through the highlights. There's a lot of text on the slides. Feel free to go through the rest of the slides on your own time. But suffice to say, there were other designs with similar capabilities coming out at the same time, which led to things like patent disputes, not to say anything about the Manchester SSEM. Eventually, one of these patent disputes caused Eckert and Mauchly to quit. Or leave UPenn. So they started a company, they started commercializing their designs. One was a failure, one was actually quite successful. This machine called the UNIVAC. And then we start picking up on IBM's story. And this is the end of our kind of rapid history lesson through computer architecture. The way to kind of think about IBM's evolution here is they started in the 50s with commercial ability being one of their first class citizen objectives. And so they started with the 701, which was the first scientific computer. They built it out of Williams tubes, which were these actually large memory units. This thing actually had quite a substantial amount of memory, and the memory was very quickly accessible. Similar to prior machines, an accumulator-based ISA, an 18-bit, 36-bit number representation in sign magnitude fixed point. And this interesting quote, Thomas Watson Sr./Jr. from IBM, upon going on the road to market this machine, he was misquoted as saying, I think there is a world market for maybe 5 computers, which supposedly led to like an ice age in computers for like a very short period of time. But this was not what he said. He actually said, I don't understand how this misquote happens. As a result of our trip selling the 701, on which we expected to get orders for 5 machines, we came home with orders for 18. Not exactly the same thing. So the IBM 701 kind of kicked things off. The IBM 650 was the first mass-produced computer, so it's kind of a lower-end system, but over 2,000 of these things were built. Here's just a snapshot of the architecture. We'll actually come back to this a little later in the class, but suffice to say, we have memory, we have a program counter register, we have an accumulator, we have a way of writing accumulated values back to memory, so basically everything that you'd expect in a modern machine. The instruction set was kind of a primordial instruction set, 10-digit decimal words. You could encode words in like several bases, and you had special instructions to compare words like in a track. There was this notion of like track locality in this barrel. To get better speeds, you'd have to be like careful about how to lay out your code so that it would be similarly placed in the track. Primordial ISA. Going further, just to like kind of talk about what more generally was happening in the ISA space. So most of what was going on here in the ISA space, building an abstraction from hardware to software, was kind of like on the simple side, just kind of adding a layer of abstraction on top of the simple kind of calculator style machines, giving you a multiply button, if you will, an add button, if you will, on top of completely disparate undercarriage architectures. And over time, as more of these machines were developed and more ISAs came into existence, it became clear that there needed to be a unification here. So we started investing in ISA design. So one of the first innovations was when the stored program computer became a thing, people started writing self-modifying code, for example, tweaking the immediate in an instruction in order to index through a loop. Instead of doing that, they invented things like index registers, like general purpose index registers. And more and more time passed, and like more of these types of innovations took place, and eventually we landed with general purpose register files, which is what ISAs today predominantly use. Okay. A brief digression around this time was this idea of, should we have ISAs as they kind of looked like at the time with general purpose registers or no registers at all, or should we have a stack-based architecture? I'm not going to go through the details of how a stack-based architecture works. Suffice to say, at a high level, the way it worked was, instead of having a general purpose register file, you had a stack, which you could push and you can pop to. So you can pop values off the top of the stack, you can push values onto the top of the stack. And the idea was to do general purpose computation with that being your interface to memory. And it turned out that you could do useful computations like complex arithmetic expressions using this paradigm. And in fact, it saved a lot of instruction encoding in space, because if the only thing you can do is push and pop off the top of the stack, you don't need register operands. You don't need to say, I want to go to register 5 or register 20 or something like that. So it led to like a very dense encoding of instructions in your program. Makes sense when the cost of storage is large. And here's just an example of how the stack machine works. And I will post some animation of this on the slides so that if you're curious about it, you can kind of take a look. But suffice to say, stacks were kind of on the table as a proposal at the time. At the same time, IBM's architecture was getting out of hand. Many specific architectures with each their individual instruction sets, IOs for interfacing with storage, assemblers, compilers, libraries. They each kind of had a market niche, and it was like N different teams not talking to one another. And so at this time, IBM started investing into research and eventually took a big bet, which led to ISAs as we know them today. So I'll just leave these words on the slide. Suffice to say, what these are principles for what IBM thought any machine should be standardized around. So there should be a general method which is machine agnostic for interfacing with different IO devices. There should be a general method for handling faults so that there's a uniform data robustness abstraction across microarchitectures. And there was a bunch of principles that they laid out. Next, they tackled the stack machine problem, stacks versus a general purpose register organization. And they noticed that, hey, stacks are only great because of fast register access, push and pop, but it doesn't really matter whether you're pushing and popping off the top. You could have just as easily just indexed, randomly accessed into like a register file, and you would have been just fine. So again, kind of like a technology-grounded argument. It turns out that making sure that the data you want at the top of your stack is pretty hard. So there's an overhead there. There's an advantage in instruction density, but it's actually for stack machines, but it's actually not so bad for general purpose register-based machines because the register files aren't that big. Finally, there's just complexities with dealing with stack machines. It turns out doing recursion, certain parts of it are more elegant and easier, but other parts are not. And so you put all of these ideas together, or all of this rationale together, and they decided for the IBM machines to go with a general purpose register file style organization. And what we landed with back then was this. And if you look at this and squint your eyes a little bit, you'll see basically nothing conceptual has changed in between now and then. We have general purpose 32-bit registers. It's like down to the number of bits in the words. Things have not changed. We have floating point registers. We have a program status word, which says whether an exception has happened. We have several different data formats. The word byte came from this kind of coalescing around a unified way of accessing data. And this was the first microarchitectural agnostic ISA, or the example of it. So there were many different later implementations of the IBM 360, but the ISA and the GPR paradigm and all of the innovation of index registers and how to handle function calls and returns, this all remains the same, agnostic to the underlying machine implementation. And this kind of kicked off computer architecture as we know today. And now we're left with the modern IBM machines, which look basically the same from a conceptual perspective as the IBM 360 did back in the 50s and 60s, and the rest, they say, is history. Okay. Now, that was our whirlwind history lesson. Any questions? You can go back and slow my voice down to your heart's content if you want to relive history at the actual pace that it was experienced at. Okay. Oh, screen sharing was stopped because the external display was disconnected. Okay, now we're going to make some headway into microprogramming. So let's dig in. So where I'm going to, is this on the screen? Okay, so I'm going to give a very brief introduction to RISC-V, but I'll assume that people have a reasonable amount of background from CS61C about RISC-V. And then we're going to, for the last part of this lecture and a good chunk of the beginning of next lecture, we're going to have some fun and kind of do a mental exercise on how to microprogram an extremely simple pipeline. First, we'll define what microprogramming is. Okay, so this was last time in lecture, and let me make sure that we're now sharing the screen again. I think what I'm going to do is I'll just do share screen, and we'll do this, and I hope that this just works when I hit. Okay, great. So last time, which is to say 30 seconds ago, computer architecture is ISA, or modern computer architecture is ISA's abstracting microarchitectural details. Applications and technology are the drivers of computer architecture. Applications influence what architecture should be doing. Technology drives how we change architectural design over time. We have 130 plus years in this space, with most of the progress being done in the last 100 years, which is remarkable. And as I said towards the beginning of the first lecture, software design, abstraction, how to scale is kind of a major factor that influences how we design the actual hardware. And finally, we ended, again, like 30 seconds ago, talking about the 360, which introduced this uniform abstraction that held over multiple microarchitectures. So now we're going to talk a little bit more about ISA design. So ISA design from 61C is the contract between hardware and software. And again, really the innovation when IBM took up the reins was to decouple the ISA from the implementation. Earlier designs had an abstraction that exposed hardware to software, but it was machine specific. So abstraction is good, but abstraction that decouples implementation and program is even better. So what these ISAs look like are typically a combination of what we call architectural state, which might be memory, or memory plus a register file, or memory plus a stack, something like this, and a set of operations that we can compose in whichever order we want, the instructions. And each operation you can think of as a state transition in a state machine. You start with some state, you execute the instruction, you get a new state. So similar idea to the Turing machine. IBM 360 was the first of these, and the main point here is that there can be many implementations of a given ISA. So it turns out that when the IBM 360 standardized its ISA, this gave the Soviets the opportunity to create code-compatible 360 implementations. Nowadays, we have AMD, Intel sharing the same ISA, x86, 64, AMD. Many mobile devices use the ARM ISA, and RISC-V is kind of like slowly creeping into this space. So there's kind of like several major players in the ISA space today. There are several ISAs, and they kind of have carved out niches in the major markets, but there are not nearly as many ISAs as there are implementations. So we're going to use RISC-V as the class ISA. So just going back, or actually one more slide on ISA to microarchitectural mapping. Something interesting is that even though ISAs are supposed to be agnostic to the implementation, they are suggestive of what an implementation should look like. So if your ISA is an accumulator, the style of microarchitecture and processor that you design is typically one that is just like very simple. It's got a little accumulator, it's like hardwired control, and that's it, because accumulators are relatively simple. If you have a CISC ISA, CISC standing for complex instruction set architecture, where each instruction in the ISA is some potentially very complicated operation, you will typically design your processor to be so-called microcoded or microprogrammed. And that's going to be the focus of the last 5 minutes or so of this lecture and a good chunk of the beginning of the next lecture. RISC ISAs, reduced instruction set architecture, where each instruction in the ISA is relatively piecemeal, simple, lend themselves better to more pipelined, hardwired control paths. VLIW, which we'll learn about later in the class, motivates the use of a simpler parallel pipeline that saves on hardware complexity. And JVMs, like the Java Virtual Machine, is like software interpreted. So these ISAs are suggestive. They don't mandate that you design a pipeline in a particular way, but they are suggestive of what types of pipelines you should be designing. That said, you can implement any type of microarchitecture, style of microarchitecture you want for a given ISA. There is nothing holding you back from doing that. And in fact, commercial designs have gone against the suggestions of their ISAs and come up with some kind of counterintuitive microarchitectures. And so kind of in the spirit of that, what we're going to be doing is designing in lecture a microcoded RISC-V machine. So I think based on time, I'm going to take us up to the LIP, the start of the microprogramming exercise, just so that we don't like give epsilon about it and then continue it next time. We'll go up to the LIP. So we're going to introduce microprogramming and then talk a little bit more about the specifics of RISC-V, just kind of a very brief review, and then we'll pick up at the beginning of next time. So why learn microprogramming? What is microprogramming? Microprogramming is an idea where you can break an arbitrary instruction in an ISA into however you want smaller operations. So for whatever operation you want to implement in an ISA, or you want to specify in an ISA, we're going to give you the flexibility to, at the implementation level, in a way that is invisible to the ISA, break that complex operation into as many small pieces as you want. So going back to a Turing machine, where every cell on the tape is 1 bit, and your action is read, write the tape, move the head to the left and the right. You can think of the Turing machine as the most aggressively microprogrammed processor ever conceived. Because to implement like a 32-bit add, you need to like do 100 some odd moves of the tape, several moves to implement each bit of serial addition, and then if it's like a 32-bit add, 32 of those operations to implement the add. And that's kind of the spirit of microprogramming. The spirit of microprogramming is I could give you an ISA with a 32-bit add, and you can implement it with a Turing machine, which is just this really simple mechanism where every bit in memory is or every location in memory is a single bit. And that's the motivation for learning microprogramming. We want to implement an arbitrary ISA with as little hardware as we have on hand. So it's kind of like a very computer architecture-y task. Given a set of constraints, how do we make something out of it? It in fact plays a big role in industry today, so microprogramming is still relevant, and so that is why we will proceed that way. Okay, so control versus data path. A little bit more about what microprogramming is. So recall from 61C, machines you can think of broadly as being control and data path. Technically control, data path, and memory, but for our purposes, control and data path are going to be the major important components. So this is like your CS61C processor, and you've got like a bunch of functionalities. You've got like a PC register, an instruction register, a register file, an ALU, maybe a memory. You've got a bunch of functionalities, and the control logic is like the marionette that is orchestrating the use of all these functionalities. So like the puppet is the data path, and like the marionette with all the strings is like all the control signals. And Maurice Wilkes and others recognized that control is usually the hardest part to get right in processor design. It's relatively easy to design the puppet, but figuring out how to pull your fingers so that the puppet looks like it's dancing on the table or whatnot, this turns out to be much more complicated because it has to be orchestrated in a precise sequence where everything is kind of timed precisely. Otherwise, the machine kind of falls out of phase and the puppet kicks itself in the head or something like that. So Maurice Wilkes invented the idea of microprogramming as a paradigm to kind of simplify this problem and provide a new abstraction for kind of interfacing with the hardware and bridging the gap between an ISA and the underlying hardware. So at a very high level, let me see where, okay, we'll get to the end of this slide and then we'll do RISC-V and then we'll do the microprogramming exercise. At a very high level, a microprogrammed or microcoded CPU looks like this, which is to say it's basically the same as a normal pipeline. It's got a data path, it's got a memory, it's got a PC register, and it's got a decoder. The main new thing about it is it's got this microcode ROM. ROM standing for read-only memory. So read-only memory, it looks like this little grid here with the holes. That's just to say that it's got words and bits in a word. So you index in the microcode ROM just like you would any normal memory, and you get whatever is in that row out. And the little circles are like ones, and the other intersections without the circles are zeros. And the point here is whenever you want to perform an ISA level instruction, what you're going to do is you're going to kick off the execution of that instruction by setting the micro PC register to what will correspond to the first of possibly many locations in the microcode ROM, making up a sequence of micro operations or micro ops that implement that instruction. So again, we have an ISA. It's made up of a bunch of ISA level instructions. Every implementation has to implement the ISA faithfully, but many implementations can map to a single ISA. What microcoding is going to do is kind of create an additional level of hierarchy to this process where, invisible to the ISA is not changing with microcoding. The ISA stays the same. The way that we're actually going to implement the computation of an ISA instruction for a particular microarchitecture is by breaking each ISA instruction up into smaller pieces. So for example, if you wanted to implement an add instruction in microcode, it might look like the following micro op instructions. Read the add or read the data required to choose where in the register file you want to read from for the add from instruction memory. Load the operand for the left side of the add to the input of the ALU. Load the right operand, left and right being the two source operands, into the second source operand of the ALU. Actually perform the addition, write back the result. So we might break up the add operation into a number of steps. You can kind of think of these as pipeline stages. So imagine that instead of actually laying out all of the pipeline stages and doing them in time one after another while other instructions are executing, we're using the whole machine to execute each one of these stages as if each one of them were themselves entire instructions, micro instructions. So that's the difference between a non-microcoded machine and a microcoded machine. Every instruction broken up into several, and we walk through this microcode ROM in order to figure out what we need to do. Why do people do this? People do this because of technology trends. Technology trends, for example, back in the day, surprisingly, logic was super expensive. ROM, RAM, read-only memory, random access memory were much cheaper. If logic is super expensive, well, then first of all, you want to implement something like the difference engine because it only has the ability to do addition. But more generally, you'd like to simplify your pipeline as much as possible. And if ROM is cheap, microcode is cheap. If logic is expensive, then microcode makes sense, because with microcode, you can implement complex functionality with simpler hardware. So with that, we'll stop. That kind of motivates the microcode exercise that we're about to do. Then we'll talk briefly about RISC-V tomorrow or 5 days from now. And then we'll do a little exercise and continue from there. Thank you all. Cheers.